Hello everybody, I hope you're doing well. Welcome back to another video in our introductory calculus playlist. So in the previous video, we've gone over the squeeze theorem as another tool for our arsenal to solve limits. One thing I forgot to mention about the squeeze theorem, which I think is very important and might help, you know, cement that concept in, is that the squeeze theorem is a powerful technique to help solve limits because if we're going to take the limit of, say, a complicated function, the squeeze theorem gives us the power to bound this complicated function between two simple functions that we can take the limits of individually. And through deducing the limits of these simpler functions, we can calculate the limit of the complicated function without even having to work with the complicated function. So today in this video, we're going to shift gears and talk about something called special limits, right? And the limit we're going to be talking about today is proving that the limit as x approaches 0 of sine x over x equals 1. Now you might be wondering, okay, so we can't plug 0 in because we'll get a 0 over 0 error, and we know that's a bad case. And I don't see any manipulation we can do with conjugates or factoring or any creative mumbo jumbo, right? But stop right there, right? You just said that we might want to try some creative mumbo jumbo, right? And you are kind of right to some extent, right? So sometimes solving these limits or proving special limits takes a little bit of creativity, and we're going to use that creativity in today's video. So what do we see in this expression of sine x over x? Well, we see a sine x, right? Now, what does sine make us think of? Well, sine makes us think of trigonometric functions, and in the previous video, or in a prior video, we've done a review on trig functions, and I've kind of linked, the sine, cosine, tangent, secant, cosecant, cotangent to the unit circle. So maybe a good starting point could be thinking about the unit circle. So on the right here, I have a unit circle here, and we notice that the radius of the unit circle is 1, and I'm kind of going to draw this altitude right here, right? So it's a vertical line that's perpendicular to the horizontal axis. So we know at point B, what this point is, right? We know that point B is going to be the ordered pair cosine theta comma sine theta because the theta is right here. And what I'm going to do is at this point right here, right where 1, 0 is, I'm going to draw another vertical line and kind of like, connect the two triangles in the special way right here. Now, the first question we need to really answer, right, is what do we notice between triangles ABE and triangles ACD, right? So what do we notice between these two triangles? Well, there's two things you'll notice. We know that the triangle ABE and ACD both share this theta, right? So that's good. We also know that angle AEB and angle ADC are both right angles. So what this tells us is that triangles ABE and ACD have two angles that are congruent, right? And what do all angles in a triangle sum up to? Well, they sum up to 180 degrees. So then you know that angle ABE and angle ACD have to be the same measure, right? Because we know that two of the angles are congruent. So the third angle must be congruent because all angles in a triangle sum up to 180 degrees. So we know that triangle ABE and ACD all have congruent angles, right? But are they necessarily the same triangle? Well, no, right? Imagine if you have a triangle that's equilateral, right? All sides are of equal length. So the angle is 60, 60, 60, right? Well, I can draw another triangle that's 60, 60, 60, but have double the side length, right? So, you know, you're still satisfying the fact that the angles are congruent, right? But the side lengths are clearly not the same, right? So what does this mean? We know that the side lengths for triangles ABE and ACD are proportional. So we know that triangle ABE is similar to triangle ACD. So this tilde here means similar. Okay, so now that we know that, right? Let's actually start kind of filling in this triangle right here, right? So I'm going to draw another copy of that triangle down here so that we have more space. So we have this triangle right here. So we have triangle A, B, E. and ACD. And what do we know? Well, we know that this side length has to be 1, and we know that this angle is theta, right? So what does this tell us? Well, in the unit circle, right? This point here corresponds to cosine theta comma sine theta. So this side is going to be cosine theta, and this is going to be sine theta. And I'm going to actually like draw another, actually, um, yeah, we don't have to worry about that. Okay. And then what else can we deduce? Well, we know that this side length here has to be 1, right? Because it's the radius of the circle, right? The radius, this side, AB and AD, are the radius of the unit circle, right? So you know AD has to be 1. Now, we can find side CD, right? We know that tangent theta equals CD over 1. So we know tan theta equals CD over 1. So this means that, you know, tan theta is CD. So you know that this side is tangent theta. Okay, so now we've jotted down all the side lengths we need for these similar triangles. And you actually will have all the ingredients you need for the proof. Now, one thing that'll make this video interesting and help you gain a lot from this is, as I go through this video, if you feel like you have an idea of where I'm going, I highly recommend you to try like, finishing the rest of the proof on your own. And then when you're ready, you can kind of like, play the video, like resume it and see, how your thoughts differ from mine and do we kind of get to the result. But I think there's one ingredient that might be helpful, right? So I want you to examine the following regions, right? So this yellow region right here, and then this blue region right here. Notice the blue's overlapping the yellow. So that is completely intentional. And finally, this orange region. So one question I think you might want to start with is, can you come up with a relationship between the yellow region, the blue region, and the orange region? I will, wait for 20 seconds, and then we can kind of continue with the rest of the proof. All right. Hopefully you have paused the video and given this question a bit of thought, and maybe you might have made progress on the proof, or maybe you might have been at a dead end. But all is well. We're all learning here, so let's finish the rest of the proof. Okay, so what do we notice here off the bat? So if we look at the yellow region, right, that's going to be triangle ABE, and the blue region is going to be like this pie right here, this pie containing ABD, right? This whole like piece of the pie right here. And the orange region is going to be triangle ACD. So let's jot that down somewhere. So we know that yellow equals triangle ABE, blue equals, ABD pi, and then orange equals triangle ACD. Okay, so we have the yellow, blue, and orange regions defined, right? So now what do we notice? Well, you notice that the yellow region is smaller than the blue region, which is smaller than the orange region. So that's going to be a critical piece of insight. So let's jot that down. So we notice that the yellow region is less than or equal to the blue region, less than or equal to the orange region. So the yellow region is represented by triangle ABE, the blue region is represented by the pi, and the orange region is represented by triangle ACD. Okay, so now that we have all these things established, we have to figure out what is triangle ABE. So what is the area of triangle ABE? The one critical insight you need to know is that the area of the triangle is 1/2 the base times the height. So because we know that the base is cosine theta and the height is sine theta, this is going to be 1/2 sine theta cosine theta. And now we have to figure out the area of the blue region. Well, the blue region is a pie shape, and this pie shape is what we call a sector, right? So we know that the area of the sector is going to be 1/2 theta r squared, where theta is in radians. For our purposes, we are assuming that the theta in that picture is in radians, so this is going to be 1/2 theta times 1 squared. So this is area of sector. And the last thing we need to know is the area of triangle ACD. Well, as you see here, the base length is 1 and the height is tangent theta. So the area is simply going to be, hold on. So the area will simply be 1/2 tangent theta. Okay, cool. So now that we have this, we can kind of start solving the limit, right? Or start getting to the value of, you know, the limit as x approaches 0 of sine theta over theta. So we know that 1/2 sine theta cosine theta is less than or equal to 1/2 theta, less than or equal to um, 1/2 tan theta. We can cancel out the 1/2s, so we can cancel these guys out. So sine theta cosine theta less than or equal to theta, less than or equal to tangent theta. Okay, now what can we do here? Well, we want to get the expression sine theta over theta, right? So what we can do is we can divide both sides by sine theta. And we're left with cosine theta less than or equal to theta over sine theta less than or equal to, so tangent is sine over cosine times 1 over sine theta. So this is going to be 1 over cosine theta. All right, so what do we know here, right? We're still trying to take the limit as theta approaches 0, right? And we see here that theta over sine theta is bounded between cosine theta and 1 over cosine theta. This should be screaming squeeze theorem at you. So what do we see here? We know that the limit as theta approaches 0 of cosine theta is going to be 1. And we also know that the limit as theta approaches 0 of 1 over cosine theta is also going to be equal to 1 because 1 over 1 is 1. So by the squeeze theorem, we know that the limit as theta approaches 0 of theta over sine theta must equal to 1. But wait a minute. Theta over sine theta is simply the reciprocal of the limit we were trying to find, right? So we know that the limit as theta approaches 0 of sine theta over theta equals the limit as theta approaches 0 of 1 over theta over sine theta. And using the quotient property of limits, we can break up the limit as such. So this is just going to be 1 over 1, which equals 1. And voila, we have proved that the limit as theta approaches 0 of sine theta over theta is 1. So we have proved the statement. And now that we have had this special limit established, we can go through some quick examples in the next video with the special limit in action. Thank you very much for going through this proof with me. And if you have any questions about how I constructed, this proof, please feel free to leave a message in the comments. Definitely like and subscribe, and hope to see you in the next video.